So where we left off was we were talking about how metals want to lose electrons so that they can have a full outer shell of electrons, whereas nonmetals typically want to pick them up in order to fill their outer shell. The examples we had used were sodium and chlorine. Okay, so sodium has 2 electrons in its first shell. It's got 8 in its second shell. And then in its third shell, it only has 1. Right? So in order to fill that third shell, it would have to find 7 electrons, which is unlikely. Okay? It's much easier for it to find a place to give away 1. Right? And for chlorine, the opposite is true. Okay? So chlorine's nucleus is there. It's got 2 in its first shell. It's got 8 in its second shell. And then it has 7 in its third shell. Okay? And that shell can hold 8. So chlorine is an element that's looking for an extra electron. Sodium has an extra electron. So they get along very well. And they form an ionic bond where, okay, one element, the metal, gives up an electron, and one element, the nonmetal, takes it. Okay? Now, that makes an ionic bond, but ionic bonds are not very strong. Okay? They basically just kind of happen, and then they can break quite easily. Right? The reason they can break quite easily is because each one of the ions that's in there now has what they want. Right? That sounds awful. Don't try and personify it, but they both got what they wanted, so there's no reason for them to stay together anymore. Again, I know that sounds awful, but okay, that's kind of how ionic compounds work. Chlorine needed an electron, sodium needed to get rid of one, and now the interaction is over. Okay, and they kind of split and they go on about their business. But they go on about their business now as charged particles. Okay? Sodium, having lost 1 electron, will now have a charge of +1. Chlorine, having gained an electron, will now have a charge of -1. Okay? So yes, they'll be separated, but now they're carrying a charge because their number of protons and their number of electrons is no longer equal. Okay? On your periodic table, if you can take that out, the one I gave you there last week, you'll notice that in the periodic table, the charges are listed in the box. Okay, so if you're looking at sodium, you can see that sodium's got a +1 underneath. Oh, and chlorine has a -1 beside it. Okay, all of the elements have those charges. You need one too? Right, so we see the charges listed beside everything. Basically, it tells you how many electrons they're either going to gain or lose when they get into an ionic compound. Those are the charges that we use when we're trying to write their chemical formulas. All right. So when we're writing the names for an ionic compound, we always write the metal first and the nonmetal second, always. Right? Because it's going kind of from left to right on the periodic table, right? And everything in our written language goes from left to right. So we write the metal first and then the non-metal second. So if we're looking at sodium with chlorine, okay, the formula for it looks like this. So we would write the name as sodium chloride, right? The non-metal always ends in "ide." Okay? And there's a reason for that. Okay? We want the nonmetal to end in "ide" because when we read the formula, then we know that this is an element and another element, not an element with some kind of complex ion. Okay? Because things that end with a complex ion don't usually end in "ide." Okay? They end in "ate" or "ite" or some other ending. Okay? So they have a different ending that indicates it's not just an element. All right, so that's the big thing we got to remember. Okay, we got to always remember that we name the metal first and the non-metal second. Okay, the other thing we have to remember is that names are never capitalized. Okay, the name of a chemical compound is a designation, not a proper name. Okay, so a proper name like John Doe, okay, would be capitalized. Sodium chloride is not a first name, last name. Okay, it's a designation. As a result, you would not capitalize it. The only time you would capitalize the S in sodium chloride is if you were starting a sentence with it. Sodium chloride tastes good on French fries. Okay, that's the only time it would ever be capitalized. Otherwise, it is not. And that's a hard habit for people to break, because I notice that a lot of grade 10s capitalize chemical names. Okay, you'll want to stop doing that pretty quickly, because they'll start being wrong pretty quickly with capital letters on them. Okay, so make sure you don't capitalize. All right, so magnesium oxide, that would be a combination of magnesium with oxygen. Okay, sodium fluoride, that would be sodium with fluorine. Okay, and then you got aluminum sulfide. Okay, would be that stuff there. How did I know what numbers to put on that last one? Evan?
Is it because of the last tiny bit, the ides?
No, because they're all ides, right? Like this is magnesium oxide, this is sodium fluoride, they all end in ide, okay? But I didn't put any numbers on these ones. Okay, what's the charge on aluminum according to your periodic table? 3, okay? How many people remember the drop and swap, or swap and drop, whichever way your teacher taught it to you, the same thing either way. Okay, so aluminum is 3+, and sulfur is -2. Right, so I write the charges up top, and then I drop and swap them. So the 2 goes here, and the 3 goes there. Right, that's how I write the formula for an ionic compound. I write the symbols, I write the charges, and then I drop and swap them. Okay, the dropping and swapping is important because it makes sure that all the charges get balanced. Okay, an ionic compound has to have a net charge of 0. That is, all the positives and all the negatives have to equal out. So if every aluminum ion has a +3 charge and every sulfur ion has a -2 charge, I've got to figure out how to get those to balance out. What's the lowest common multiple of 2 and 3? 6. Okay, 3 times 2, +6. -2 times 3, -6. Did this just work out to 0? Yeah, the positives and negatives cancel out. That's why we drop and swap it. Make sure that that always works. Okay. Is that ringing a bell for everybody? Hopefully that's somewhat familiar. Okay. All right, something that's new. Okay, sorry. Names are never capitalized. That might be new. Don't know if that always necessarily gets stressed. Okay, charges are positive on metals, negative on non-metals, and they're always listed on your periodic table. Okay, so in this case, we knew that aluminum chloride should be AlCl3 because aluminum is +3, chlorine is -1. When we drop and swap, we end up with 1 and 3, but we never write the 1s. Okay. Okay, so this is also something here that's important. A true compound should have a net charge of 0. Okay, and you can write that's why we drop and swap. Now, that compound there, that aluminum chloride, it's got 3 chlorines in it. How come I didn't say to people there's 3 chlorines there? Why didn't I write that as aluminum trichloride? When do I use prefixes like di and tri and tetra and hexa? I only use them in molecular compounds. Never use them in ionic. Okay, we never use prefixes in ionic compounds because there's only one way that these 2 elements can go together, where the net charge would be 0, and that's if there's 1 aluminum and 3 chlorines. There's only one way they can go together, okay, because the charges have to balance. That's why we don't need prefixes in an ionic compound. Okay, they're redundant. In a molecular compound, because electrons are being shared, we have to put prefixes on because we have no idea how many of everything there is, because it could be any number. Okay, questions so far on the naming part? All right, I want you guys to write these ones down and then try and write the proper names for those. Let's just go to number 6 for right now. Okay, so let's go to number 6. I'll let you get ahead of me, and then we'll go through them together. Obviously, we've done this one already. Okay, we want to name the metal first. The metal is sodium. And the nonmetal is chlorine, which we changed to chloride. All right, no capital letters. Then for number 2, okay, my metal is K, which stands for potassium. And F stands for fluorine, which we changed to fluoride, right? Potassium fluoride. All right, give you a couple more minutes to get up to number 6, then we'll look through the rest from there. All right, let's look at 3 and 4 here. So in number 3, I've got H, which stands for hydrogen, and I've got I, which stands for iodine. Now, which one of those is the metal? I mean, they're both gases, but what side is hydrogen on? Actually, hydrogen's only on this side. It actually can behave as a non-metal as well, but most of the time it behaves as a metal, even though it's a gas. Okay? Hydrogen is actually the most metallic substance there is, even though it's a gas. It just happens to have an incredibly low boiling point. Okay? We can get solid hydrogen if we get it cold enough or we put it under enough pressure. Okay, but it is a metal, even though it's a gas. Okay, metal is not so much about being metallic, like feeling metallic, as behaving in a metallic way. That is to give up electrons. Okay, the more metallic you are, the more easily you give up electrons. All right, so we've got hydrogen here, so we're going to name this hydrogen iodide. Okay, the way you can tell whether hydrogen is acting as a metal or a non-metal in a compound is this. If it's listed first, hydrogen's behaving as the metal, because we always list the metals first. Okay, if it's anything other than first, it's behaving as a non-metal. Right? Okay, number 4, I've got Ca, which stands for calcium, and Br, which stands for bromine, right? So this is going to be calcium bromide, right? I don't need a prefix in there. We don't use prefixes in ionic compounds. There's only one way for calcium and bromine to go together, because calcium's a 2+ and bromine's a -1. They can only go together as CaBr2 and have their charges balanced. Evan.
Like you said, because of number 3, that how two of them are, is it ionic or is it non-ionic?
It's ionic, because hydrogen's behaving as a metal.
So no matter if you use hydrogen, it's ionic?
No. In this situation, hydrogen's acting as a non-metal.
Oh, okay.
It's listed second. That would be a molecular compound.
Okay.
Yeah?
So if it's listed first.
If it's listed first, it's behaving as a metal and it's an ionic compound. Yeah. All right, for number 5 here, I've got Al, which is aluminum. And I'm going to continue to pronounce it that way and spell it that way, even though the International Union for Physics and Applied Chemistry has said that it is actually supposed to be written and pronounced as aluminium. It is stupid. Okay? I do not drink pop out of an aluminium can. I do not drive an all aluminium truck. It just sounds silly. Okay, so aluminum. I'm going to say it that way. Okay, all right, aluminum, and then At stands for astatide. Okay, and for number 6, Cs is cesium, and S stands for sulfur, which we changed to sulfide. And I don't care whether you spell that with an F or a PH, either one is fine. Okay? On your periodic table, it's spelled with an F, so you can go with that. All right, questions so far? Is it all right so far? Okay. Okay, try the rest of those, and we'll go over them here in a few minutes. So for number 7, Na stands for sodium, and O stands for oxide. So this is going to be sodium oxide. Okay, for number 8, Ba is barium, And Se is selenamide. Okay, so this is just going to be, or selenium, so it can be barium, either selenide or it could be selenamide. Selenamide. Okay, either one. Okay, most of the time people just write it selenide because it's shorter. Right. For number 9, Ra stands for radium, and Te is for tellurium, so this is radium telluride. Number 10, we got lithium with fluorine, so this is going to be lithium fluoride. And number 11, we've got rubidium with sulfur, so this will be rubidium sulfide. And for number 12, Sr is strontium and I is iodine, so this is strontium iodide. Okay, and then for number 13, calcium and oxygen together will be calcium oxide. And number 14, magnesium selenide. All right, questions on any of those? All right. Next thing we need to look at is what happens when this happens, right? I get a compound like this, iron oxide. Look on your periodic table in iron's box. Iron can be a 2+ or a 3+. So that means that iron oxide could be two different things. Oxygen's always a -2. So this would be FeO, right? When we drop and swap, we get a 2 here and a 2 there. But since they're the same, we just cancel them off, okay? Or we can drop and swap this, and we end up with Fe2O3. Here's the problem. Those two compounds are not the same, but they would have the same name. Can we see any problems with that? We could mix them up. Yeah, okay. Especially considering that one form of iron oxide is rust and it's fairly harmless, and another form of it can be quite poisonous. Okay, so if I was talking about my experiment on, finding the nutritional value of iron oxide and having people, not that people would do that, but they're consuming rust and, that's helping their hemoglobin or red blood cell production or something stupid like that. Okay, just say I was doing that, and I just write in my whole paper about iron oxide, and somebody reads my paper and says, oh, I better try that, eats the other stuff and dies, I'm kind of at fault for that. Okay, so we've got to have some way to distinguish which charge of iron is being used in the name. Otherwise, I've got two things with the same name. If you've ever been in a class with two people with the same name, that can be a problem. Okay, it's just fortunate that most of the time they don't have the same first and last name, although I have had that happen. I had two Chase Andersons in the same class one time. Weirdest thing. Okay, especially when you're marking their tests. Okay, Chase Anderson, oh, I don't know, you guys figure it out. Which one's yours? I actually started putting like 1 and 2 beside them so I could keep them straight, right? So we obviously, that could be a problem. So we need to have some way to tell people, I use the iron with the 2+ charge, or I use the iron with the 3+ charge. The way we do that is we put a Roman numeral in the name beside iron that is equivalent to its charge, all right? So if I was using this iron, okay, this would be iron 2 oxide, and this would be iron 3 oxide. Okay, because this compound uses the iron with the 3+ charge, this compound uses the iron with the 2+ charge. Okay, so we would write iron with the proper Roman numeral and then whatever non-metal it was with. Okay, so what would the name of this stuff be? Right, so copper or Cu stands for copper. S stands for sulfide. So this is copper something sulfide. What are the two possible charges for copper? 2 and 1. So copper can be a 1 plus or a 2 plus. Both are listed there in the box beside copper. Okay. The one that's listed first, incidentally, is the most common. Okay. One is usually more common than the other. All right. What I got to figure out then is this the copper with the 1 plus charge or the 2 plus charge? How am I going to figure that out? Well, but I'm trying to figure out the Roman numeral. How do I figure that out with just this formula? How do I figure out what charge copper has? Okay. Does sulfur only have one possible charge? Yeah. Sulfur is always -2. All right. We know that ionic compounds have to add up to 0. So what's the only possible charge for copper that'll make this compound come out to 0? 2. Right? That's what I do. That's how I figure it out. I always look at the non-metal and figure out, okay, what charge would the metal have to have in order to make this work? Well, this would have to be the copper with the 2 plus charge. So this is copper 2 sulfide. I know you had it figured out. It was just hard to put into words. Okay. All right. What about this one? What would the name of that stuff be? Okay. The name of this stuff is lead 4. That's IV. Lead 4 oxide. Here's what happens though for a lot of people. They see that 2 there and they just go, oh, well, it must be lead 2 then because there's a 2 here. Not necessarily. I always look at the charge of this stuff. Every oxygen has a -2 charge. And how many oxygens are there in this compound? 2. That means there's a total of 4 negative charges in this compound. I only have 1 lead atom here. So this must be the lead with the 4 plus charge, not the lead with the 2 plus charge. Okay, that's what I've always got to go with. All righty, is that making a little bit of sense? That's new. You would not have learned that in Science 9 most likely. Okay, using Roman numerals for what we call multivalent metals. That means they can lose different numbers of electrons when they form an ionic compound. Okay, this lead can lose either 2 or 4. Okay, iron can lose 2 or 3. All right, so that's what we just went over here. This is just the notes version, the word version of what I just talked about there. Okay, so we've already done that. All right, so I'm going to have you guys try these ones. These all require Roman numerals. And we've already done number 1, but it won't hurt you to do it again. Okay, let's do 1 through 4 for right now, and then we'll go through them together. All right, let's walk through at least the first 2 here. All right, so for this one here, I've got iron and oxygen. So I know it's going to be iron something oxide. So I can write that much at least. Okay, then I've got to figure out which Roman numeral is going to go on this iron. So oxygen is always a -2. And how many oxygens are there? 3. So how many negative charges in total? 6. Okay, so this compound has 6 negative charges. I need to get 6 positive charges out of the 2 irons. So what's 6 divided by 2? 3. Okay, this has to be iron, Roman numeral 3, oxide. Now, I know probably a few of you are looking at that and going, okay, couldn't I have just like reversed the drop and swap and that would have told me the right answer? And the answer is on this one, yes. Works about 2/3 of the time. Okay. I like ways that work all of the time. That's why I'm showing you this way with the numbers. Okay. If you just reverse the drop and swap, you're going to get compounds where that doesn't work. Okay. And you're going to get the wrong charge and then get the wrong answer as a result. Okay. Let's look at number 2. So we got cobalt. And that's what CO is with sulfur. So we got cobalt something sulfide. Charge on sulfide is always -2. So what's the charge on cobalt? +2. So this is cobalt, Roman numeral 2, sulfide. Okay. For number 3, we've got Mn, which is manganese. Okay. And it's with chlorine, so this is going to be manganese something chloride. Chlorine's always -1, and there are 4 chlorines, which means there's 4 negative charges in total. I only have 1 manganese to offset that, so the charge on this manganese must be 4, right? There's only 1 of them, so it has to have a charge of 4. Okay. Incidentally, if you don't know the Roman numerals, I, IV, V, VI, VII. You probably won't need to go past that for the charges. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay. Yeah. This is why the Roman Empire fell. They had a bad numbering system. Yeah. Anyway, okay. Number 4, we got copper with sulfide. I think we did this one as well. Okay, so we've got copper something sulfide. Sulfur is always a -2, so there's only 1 copper here. It must be the copper with the +2 charge. All right, I want you to try the rest of these, and we'll go over them in a minute. So for number 5 here, SN stands for tin. So that's going to be tin something telluride. Okay, telluride's always a -2, so that means this tin must be +4, so this is tin 4 telluride. Okay, and then we've got Hg, which stands for mercury. And it's with astatine, so it's mercury something astatide. And then we've got, there's 2 astatines, and what's the charge on astatine? Always -1. Okay, so that means there's 2 negatives, so this must be the mercury that is a 2+ charge. Okay, don't be afraid to ask questions as we go along here, guys. Our next one, we've got polonium with iodine, so it's polonium iodide. Iodine's always a -1, so that's 4 negative charges that have to be offset by 1 polonium, so it must be polonium 4 iodide. Okay, and then we have antimony with sulfur, so it's antimony sulfide, and sulfur is always a -2. There's 3 sulfurs, so that means there's 6 negative charges here. That means if I want to get 6 positives, the antimony must have a charge of +3. Okay, so it's antimony 3 sulfide. All right, number 9, we've got nickel with nitrogen, so this is going to be nickel something nitride. Nitrogen's always a -3, and there are 2 of them for a total of 6 negatives. If I'm going to get 6 positives, 6 divided by 3 is 2, so this is nickel 2 nitride. And then lastly, we've got ruthenium with oxygen, so this will be ruthenium something oxide. Okay, oxygen's always a -2, so the charge on ruthenium must be 4. Okay, questions on how that works? Okay, basically we're just trying to find which charge goes on there. All right, what if I ran into this situation? Okay, all these other compounds that we looked at, how many elements were in them? 2. How many elements are in that compound? 3. How am I supposed to name that? Right? Our rules only go with when there's 2 things. So am I supposed to call this sodium oxygen hydride? The answer is no, don't do that. Okay. What we want to do, anytime we have more than 3 elements in an ionic compound, if you look on your periodic table, above the periodic table, you will see the table of complex or common, polyatomic ions. Okay. In there, you will find some ionic, or some ions that have more than 1 element in them. Okay. So if I'm going to name this stuff, the metal is still the metal. It doesn't change. It's going to be sodium. But then I got to find OH. Is OH in that table? And what's it called? Hydroxide. Okay? That's all we have to do. You don't have to change the ending to "ide" or anything like that. You just find it in the table and write its name exactly as it appears. Okay, so we could have, let's say, something like this. Okay, so if I'm going to write the name for that, okay, what's Ca stand for? Calcium. And NO3? No, sulfite. NO3. NO3. Nitrate. Okay, nitrite is NO2. Okay, so NO3 is nitrate. All right. Now, looking at this formula here, what have we got brackets on here for? Right, okay. I've got to put brackets around this so people know that this 2 applies to all of this, right? To the entire nitrate molecule. If I don't write that, then it looks like this. Does that mean the same thing? Okay. In this compound, there's 1 calcium, 2 nitrogens, and 6 oxygens. In this compound, there's 1 calcium, 1 nitrogen, and 32 oxygens. Not quite the same thing. All right? So just like in math, we use brackets to group things together. Right? So the 2 outside the brackets means there's 2 nitrates. Now, how did I know I needed a 2 out here? Well, when I would have been writing this formula, I would have dropped and swapped. The charge on nitrate, if you look on your table there, just has a dash beside it. That means it's -1. Okay, calcium is a +2. So when I drop and swap, the 1 would go here, and I wouldn't write a 1, and the 2 would go here. And then I would say, all right, I got to put brackets around that so it's not O32, okay, so that it's NO3, 2. Okay. That's just that dropping and swapping thing we talked about before. All right. Yeah. Okay. Does that make sense with the polyatomic ones? All right. All right. Let's look at molecular ones now.